to part 2, which will be on the UHF RFID or metal tech antenna design. Right. So okay. So of course, right, RFID is employed everywhere in the market, in the commercial market, right? So for particularly, right, for this UHF stands for ultra high frequency, which is covering, right, from 860 megahertz to 960 megahertz, right, depending on which country you are in, right? So if you are in the European band, right, is covering the 866 to 867 megahertz, right? And for the US, right, is covering from 902 to 928 megahertz. So particularly here today, right, I will share my research work on the metal tech antenna design. So okay, now here, and of course, right, this RFID technology, it has been rapidly developing, right, in the past many years, right? Actually, this one is already a very popular and very common technology, right, in the market. So that this RFID, right, it has been applied in many places. For example, right, your electronic tolling, your passport, actually inside passport, right, there is an RFID tag. And of course, right, for waste management, for access control, and also, right, for human and animal identification. Needless to say, right, for asset tracking and management, right, people are using RFID. Okay, now here, on this page, you are shown, right, with the basic working principle for this RFID technology, right? So basically, for this RFID technology, RFID system, right, you have two parts. So that the first part is a tech antenna, right? So that this tech antenna, it consists of an antenna and a chip, right? So the other part, right, is what? Is the reader. So that over here you have a reader antenna, right, which is connected to reader, right? So after you have acquire, right, the signal, the information, right, from the tech, right? So that the information will be sent to the reader. So that, right, the reader will send the information to the computer, right? And of course, right, you later on you can process the data in IoT. You even send to the cloud and so on, right? So on this page, you are shown, right, with some of the popular texts that you have seen outside, right? I think, right, this is everywhere, right? Okay, on top here, right? So why people are using this UHF tech antennas? Because first of all, this UHF tech antennas, right, so that it is working in the microwave range, right? So that, right, because in UHF, so it's covering from 860 to 960 megahertz. So because of the high frequency, right, it has a faster data rate. And it's because it's antenna, right, it can be made very small in size, light in weight, and of course, right, the read range is much faster than those HF, right? And of course, right, I believe that all of you have seen those coil, right? Those are working at 13.56 megahertz, right? So that the frequency is lower. But for this UHF, since the frequency is much higher, so of course, right, the data rate is much faster. And of course, right, all these tech, they can be mostly fabricated by using the standard PCB technology, right? So that it's very easy to fabricate as well. So here is showing you, right, some of the problem that you have, right, when you are designing a tech, right? So that, and of course, right, since a tech, right, you have to attach it on an object, right, on an item or a commercial item, right? So that, right, it has to be very low in profile. And of course, right, but however, right, if you are using a dipole antenna to become a tag, right, to design a tag, right, so because then, right, the size will be pretty large. Why? Because the conventional dipole tag, right, is working in the half lambda or quarter lambda, right? So because of that, right, so the size, right, is bulky, right? So okay, so and of course, right, a lot of the tags in the market, right, they are very short in the read range. So that, right, our tag here, particularly for metal, right, we are applying some technique, right, to extend the read range. And of course, right, so the conventional antenna, right, usually is made on hard and rigid this substrate, right? So that, right, it's not flexible. But you please bear in mind, right? So some of the objects, they may be curvy, right? They are not flat, right? So that your RFID, right, it may have to be flexible and so on, right? So, and of course, right, so designing tech, right, sometimes can be quite tedious and time consuming, right? So our research here is also, right, to provide some very efficient, right, tuning technique that can be used, right, to facilitate the design of tech antenna. Okay, the objective here is what? We want to apply some miniaturization techniques for design electrically small and some flexible antenna, right, where the read range can be made right beyond 9 meters. And of course, right, we will explore some new way and impedance tuning techniques for designing this antenna, right? So, okay, of course, right, we have many techniques that can be used to design or to miniaturize the antenna size. But of course, here, right, I'm only sharing 2 cases. So the first one that we are sharing here is the compact ring antenna with a high impedance line loaded, right, with distributed inductors for this ohmmeter tech design. So, okay, you can see that, right? This is the antenna structure that I am proposing here. So basically, this is the tech antenna. So over here, you have a ring, and on the ring, right, you are loading it with 2. This is actually, right, the distributed inductors, right? So that, right, so since you are loading it with these 2 distributed inductors, right? So that, right, the antenna size, the ring size, right, can be reduced significantly, and of course, right, the distributed inductors, right, is also providing inductances to the antennas. And of course, right, in my research work here, I have shown that, right, okay, you are loading here and loading here, right? Actually, right, you can design the inductance quite accurately. Okay, here is showing you the antenna footprint, right? The antenna prototype after the fabrication. So this antenna, right, it is made on a very thin copper film, right, which is deposited on the PET with a substrate thickness of 0.05 mm. And of course, right, this we have engaged a flexible form right in between, so that right, this antenna is slightly flexible. And of course, right, over here you can see we have a chip here, right? We have employed the U-Core 8. Okay, here. And of course, right, after fabricated the antenna, we have a measure the read pattern, right, in the XZ and YZ plane, right? And also as well as the XY plane. You can see here it's a linearly polarized, right? So that, right, the read distance in principle, right, it can go nearly 9 meter here. And of course, right, in the measurement process, we have followed the US standard, right, which is a 4 watt. We have used a 4 watt EIRP power, right? And of course, right, this measurement is performed using the Performance Pro measurement system here, right? And of course, right, in other measurement, we have fixed the reader at a position, right? So that, right, we just rotate the antenna, the tech antenna. So of course, right, after the measurement, we have obtained, right, the read distances, right, for different kind of commercial products. And all here, right, all of this measurement measured in the ball side direction, right, which is theta of 0 degrees here. Okay, now, so for this I have a mini summary for design 1, right? So, okay, so for this tech design, this miniaturization, right, is achieved, right, through the incorporation of distributed inductors. And of course, right, we have a T-match at the feet over there for improving, right, the impedance matching. So, and of course, right, this antenna is able to achieve a maximum read distance of about 9 meters, and it's flexible, of course. Okay, now I'm sharing with you my second design, right, which is implemented using a complementarily coupled, right, C-shaped microsweep patches. This what's so special about this tech? It can perform a very broad range of frequency tuning capability, right? And of course, right, it can be used for ohmmeter application. So on this slide, you are shown with the antenna configuration, right? So what do you mean by the complementary C-shape? So over here, you have one C-shape, another C-shape here, right? And of course, right, in the middle, you have a very narrow slot here, right, which is providing the how to say a very high inductance, right? What for this tag antenna, it can be fully implemented on one layer, right? On the reverse side, actually is a ground, right? Of course, right, in the actual application, right, you are attaching it on metal, right? So that, right, actually this ground, right, it will be connected to metal as well, right? So effectively, right, the radiator is only implemented on a single layer. So here is showing you the current distribution, which is simulated using the CST, right? So that you can see here, okay, the current on the external ring, right? split ring, right, is in this direction. But that on the internal ring, right, is in the opposite, right, when it's very near to the edge here, right? So it's actually, right, it's complementary to each other. There's a reason why, right, we're calling it a implementary coupling scheme, right? So, okay, now here. So when, okay, this I5 is shown here, right? I5 is the gap here. So that, right, when you are varying the gap here, you will find out that, right, actually, right, the frequency, it can be very so much, right, from 0.86 or 86 megahertz up to 96 megahertz. And of course, right, we have even perform the tuning over even a larger range, right, up to 1.2 gig, right, which is still, despite the frequency is tuned up significantly, right, and yet, right, the power transmission coefficient, right, is still it can be still maintained well above 0.9, right, which is very, very good. So on this slide, you are shown with the measured read distance, right, for this tag in the XZ and YZ plane, right? So in principle, right, it is a broadside antenna, right, which is radiating to the both sides. And of course, right, this is the antenna pattern in the XY plane, right? Of course, right, this in this measurement, right, actually, right, we put a tag here and we're placing, right, the reader antenna on top. So actually, right, this showing the polarization of the antenna, right? So you can see that, right, it's linearly polarized. So of course, right, we have also tested this antenna on a couple of commercial products, right? You can see that, right, these are containers. We are placing it on different containers, right? For all cases, right, all the frequencies are actually, right, very, very, very stable, right? This is actually, right, a very good feature of this antenna. Okay, now here, so I have this mini summary for this part, right? So this antenna, this tag antenna, it can be implemented, right, on a single layer, right? And it can achieve a very broad range of frequency tuning, right? So that, right, the coupling mechanism, right, it can generate sufficient reactance, right? So that, right, this tag antenna, it can be how say, it can provide sufficient impedance for good impedance matching over a very broad bandwidth. And of course, right, it can achieve a very broad very far range as well. Okay, now, right, I want to show you the impedance matching which is performed on the bird VNA and the rod and sword VNA, right? So please bear in mind, I show again here, right? You can see that, right, this antenna here, I click back here, right? Basically, the antenna here, there are two ports, right? You can see that, right? There are two ports here. And of course, right, the impedance that we want to measure here is actually, right, the differential impedance, right? So there's a reason why, right, in the the impedance measurement, we have engaged a differential prop here, right? And we have performed the measurement, right? Okay, this is you can see that, right, there is a differential prop here, which is fabricated by our own, right? It's a housemate, housemate, right? This differential prop. And of course, right, we have performed the measurement using this rod and sword VNA as well as this bird VNA, right, for getting this differential impedance. So you can see that, right, in the measurement, right, you are placing the prop, the differential prop, right, on the antenna. And of course, right, they are connected, right, to the two ports of your VNA. So that, right, after acquiring the data, right, actually you can obtain the impedance on the laptop here straight away for this bird VNA. Okay, now this is showing you, right, for the prototype number 1, right, you can see that, right, okay, we of course, right, in the impedance measurement, we have to first remove the chip here, right? So we are placing our differential prop across here, and we have measured the input impedance, right, for the bird VNA as well as the rod and sword VNA, right? So in principle, right, both of them, right, they are the agreement, right, is quite well. Although they cite discrepancy, right? Actually, right, this discrepancy, right, is caused by the placement of our prop. Because you can see that, right, when we are doing the measurement in the first round, right, using the rod and sword, okay, let's say we are placing the prop across here, right? So after that, right, we remove it, right, when we place it using we perform the second measurement, right, by using this bird VNA, right? And of course, right, it was moved there is slight fluctuation, but in general, right, they are going very well, right, around the resonant frequency. Okay, now here, and this shows the same, right, for the antenna number 2, right? So that, right, you can see that, right, for the bird and rod and soft VNA, right, basically they are capable to measure the impedance very, very well, very, very well. And of course, right, this can also, right, can measure the differential S parameter, S11 for sure, right? If you want to get the differential S parameter, you can just process the single-ended S parameter, right? S11, S22, S12, S21, for example, right? And you can get the S11D and S22D and S12D and S21D, right? Straight away on the computer, right? Okay, so now, right? So this is my final slide, right? So here is showing you, right, our measurement that are performed, right, using the rod and swat and also the bird VNA, right? So then, of course, right, for our rod and swat VNA here, which is the ZVR model, right? The measurement setup, it has to be performed, right, through the physical push-through button, right? Of course, it has a screen, right? But for this bird and VNA, right, it is connected to a laptop, right? So that everything, right, can be acquired on the laptop straight away, right? So for the VNA calibration process, right? So for this rod and swat VNA, it has to be performed through this manual calibration. But for this bird VNA, right, it can be the calibration, it can be performed through electronic as well as manual, right? Both can be performed easily. So that, right, for the measurement graph scale and display option, right? So for this rod and swat, the result is directly displayed on the machine LCD, right? Of course, right, if you want to do some processing, right, you always have to copy the data out, right? And through a pen or whatsoever, right? And later on, you can process it, right, through the computer. For this bird VNA, right, since it's straight away communicated to the computer, right? So that, right, you can process, even you can program the VNA straight away through the computer, right? So for the measurement, right? So this rod and swat is a 2-port. For this bird VNA, right, is a 4-port. You can see the convenience, right, when we are performing the measurement, right, for this MIMO, right? Because the MIMO, you either have 4 ports, 8 ports, right? So that for this bird VNA, right, you can do the measurement, right, very conveniently. If you have 4 ports, you can do it in one shot, right? If you have 8 ports, of course, right, you need to use less matches. So okay, now, so that for the data import and export, so that for this rod and swat, right, you have to export to a mobile storage device or internet, right? So that for this bird VNA, right, you can straight away save your data to this laptop storage, right? After that, you can straight away send it to the cloud for further processing and so on, right? But for both cases, right, actually, right, you can see that, right, the bird VNA, the result, right, is as good as the rod and swat VNA. Both are producing, right, very accurate measurement. And of course, right, the signal level can go down, right, to almost 50 dB, still with very good accuracy and very good resolution. So I think this is the final slide that I have. Thank you very much.